Hello 20-2 students. So today we're looking at lesson 7.1. So maybe working backwards a little bit because if you remember our last lesson was 7.2. So in that lesson we looked at solving quadratic equations by factoring them. And now we're kind of stepping back a little bit because we had looked initially at when we looked at the quadratic equation in standard form, we looked a little bit at working with our calculator to solve it. So we're just going to kind of extend on that a little bit today and look at maybe some more complex examples. So just a little bit of a recap, remembering our basic standard form for the quadratic function, and just remembering that when we're trying to solve it, basically what we're looking for is the x-intercepts. So that means the values of this equation for which y is equal to 0 or the function of x is equal to 0. So of course the function has an infinite number of y values based on whatever x values you could enter, but the equation when we set it equal to 0 is only going to accept that one y value, and so we're just looking for the x values that would make that true. So basically that's our job when we're solving these equations. So zeros are the values of the graph that make y 0. Remember, like we talked about last time, they can be called roots or x-intercepts, and often when you're asked to find them, you're being asked to solve the equation. So just being familiar with that terminology. Now we've already looked at how to determine the zeros by graphing, so I'm not going to go through the whole recap again, but of course it's written out there for you if you need it. So let's just go through a couple of quick kind of like easier examples again to remind ourselves of how to solve these, and then we'll get into, something a little more complex. So in this first one we have 4x squared minus 12x plus 0. So just remembering how to enter that in. 4x squared minus 12x plus 0. Then we go to our graph, and of course my windows are all weird, so I'm going to go to zoom, and I'm going to choose standard. And let's see if that gives us anything helpful. Looks like maybe not. Not sure why that's not graphing. All right, calculator froze up there for a second. So we see our graph, and just remembering that if we're asked to graph it, find the zeros, and state the number of roots. So this is something kind of new. Stating the number of roots is basically just saying for this parabola, how many points does it cross the x axis at. So for this one, we can pretty clearly see that it has 2 roots, right? Because we can see the parabola crossing the x-axis twice there. And then just remembering that when we're looking for the zeros, we do second function trace 0, and we would go left bound and right bound, guess. So our first one is at 0, 0, and our second one, you guys could probably actually just count this 1, 2, 3. Our second one is at 3, so let's say maybe there. And then if we wanted to sketch the graph, the other main point we should know is the vertex. So let's just go minimum in this case, and left bound, right bound, and we see that the minimum is at 1.5 and y is -9. And actually this is a good point, so then we can just kind of connect our dots. Of course, if you're sketching and you're trying to be more precise, you could find more points on the graph. But this is actually a good time to point out like a quality that we see with these quadratic functions that can become useful as we move on and we have to start trying to like sketch out these graphs or think about the different points. And so if you remember in our first lesson in 6.3, we talked about an axis of symmetry, and we talked about how the x component of the vertex is basically going to divide our graph into 2 kind of mirror images of each other. So one thing you could do, like if you're given the vertex and you're given one of the zeros, so we know that our vertex is at 1.5 as an x value, and then -9. And we know that our other 0 was at 3, 0. So what we could do here, if we needed to find this other 0 and we didn't have a way of finding it, all you would need to be aware of is that everything on either side of this axis is going to be a mirror image. So if one x-intercept is 1.5 to the right of the vertex, the other x-intercept is going to be 1.5 units to the left, so that means it'll be at 0, 0. Okay, so it's helpful if you're trying to graph to remember that the vertex is always this mirror of symmetry. So if you find one point on one side of it, the y value, when the y value is the same, the x value will be the mirror image on the other side of that, on the y value. So for this one, we would say our graph has two roots, and they are x equals 0, because this one was 0, 0, and x equals 3. Okay. Going to the next one here, we have y equals 3x squared. 3x squared. Oh, I'm just going to delete that 3x squared plus 11x minus 4. Go to our graph. And so here we're kind of cut off a little bit. Honestly, I'm not going to worry too much about the vertex for this one because we don't need to know it for this question. So I'm just going to kind of go like this. And so we can see that our one intercept is at -1, 2, 3, 4. Of course, if you want, you can always check. Sometimes if you just trace, oh no, it's not going to do it for us. Second function trace, we want to look for the 0, left bound, right bound. I would always recommend confirming, even though it looks like it was, and it was. Sometimes it's like off by a little bit. So -4 and 0. And then on our other side, second function trace, 0. We're going to go left bound and right bound. And we find that the other 0 is at 0.3 repeating, so that's 1/3, and y equals 0. You could have also written this as 0.3, and then if you put a horizontal line above the 3, that represents that the decimal is, like that number value is just repeating endlessly, and then 0. But if you know your fractions, it's better to write it as an exact value, which is what a fraction is. So again, we see that this parabola crosses the axis at two separate points. So that means this graph has two roots, and they are x equals -4 and x equals 1/3. Okay. For this last one, we have x squared plus 3. And this is a little bit of a different graph. So if we look at it, what happens here? Well, we see that our graph has a vertex at 1, 2, 3 on the y-axis. So let's just say there. And then it just goes upwards from there. So then we need to ask ourselves, will this graph ever cross the x-axis? Well, obviously not, right? This is called the minimum for a reason. It's because the graph doesn't go any lower than that. So if the minimum is located above the x-axis, that means we're not going to have a time where this graph crosses the x-intercept. So then we say there are no roots or no solutions to this equation. If you were to have a graph like this that had its vertex right on the x-axis, and then it goes like up away from there or down away from there, that would be an example of a problem with only one solution. And I think we'll see that on the next page. Yeah, we do. Okay, so let's try some more advanced examples here. So in this one we have 4x squared equals 7 minus 27x. The problem with this, like I mentioned in the last section, is that in order to solve any quadratic, we always have to have it set equal to 0. So that means, like for me personally, I like to keep my a value positive. So I'm going to move everything over to this side to be with my x squared. Okay, so I'm going to do -7 and plus 27x. And I'm going to do that to both sides, but I'm not going to write that out again. So basically I end up with 4x squared minus 7 plus 27x. If you want, you can rewrite it in the, the normal form we use, but it actually won't matter when you enter it into your calculator. So now if I go into my calculator and I put in 4x squared minus 7 plus 27x. If you want to try putting it in with the 27x first and then minus 7, you'll see that we end up with the same graph. So 4x squared minus 7 plus 27x. Huh, that's funny. When I did my filled in notes, I don't know what I entered in there because I just ended up with a different answer. Alright guys, I don't know why the filled in notes I had a different answer. I'm not sure what I did there. I guess I should have double checked before I wrote them down and filled them in for you. So just ignore what's on the filled in notes for this one if you're checking them. So I can see my window. I'm going to want to... Actually, you know what? I don't even care about the vertex on this one. So let's go and just solve for our zeros. So second function trace, 0. Oops, there we are. Okay, so left of the x-axis, and then we want to go right of the x-axis and guess. So we're going to be at x equals, of course this means I drew out my graph all wrong too. Oops. So I'm going to switch this up and put my y-axis over here. Okay, so I'm at x equals -7. And then for my other one, second function, trace 0, go left bound. Where am I? Y equals... Okay, left bound, right bound. Okay, so x equals 0.25. Shoot, kind of made that really far away. Whatever. So this is going to be my graph, right? And it's going to go down out of sight, and it's going to kind of come back up this side and keep going up like that. That's terrible, but so I would say -7, 0 here, and 0.25, 0 over there. And so it says just graph them to find their zeros, state the number of roots each equation has. So 2 roots, and they are x equals -7 and x equals 0.25. Same thing over here. We want to make sure that we have the equation set equal to 0. If you have a positive a value, I always recommend you keep it that way. So now this time I'm going to again move the 1 over by adding it to both sides. So that's going to give me 25x squared minus 10x plus 1 is equal to 0. So if I put that into my equation here, 25x squared minus 10x plus 1. Hopefully I got this one right on the one I gave you guys. Yeah, it looks like I did. Okay, so now I might actually just shrink that in a little bit so you guys can see that better. So I'm going to do my y minimum -2, 5, and -5. That makes it a little more zoomed in. So now this is the kind of equation I was talking about where we see, I'm pretty sure that the vertex there would be, if we put in a 0, left bound, right bound, enter. And we see that our vertex for the graph is the same as our 0, right? So when y is equal to 0, we end up with x equals 0.199 repeating. So I'm just going to say 0.2. So right there, I'm going to have 0.2, 0. And then my graph is just going to kind of go up like this in either direction. And so for this one, because our vertex is at the same point as our x-intercept, and it's only 1, we would say there is 1 root to this equation, or 1 solution. Now, this last one is quite a bit more complicated because when we have 2 equations that are set equal to each other, what we want to do, so this is like if you have something quite a bit more complex than just like, you know, 1 number or whatever that you need to move over, or 2. Like, so we have a whole kind of set up here and a whole set up there. And so basically what we want to do in this situation is set these up as 2 separate graphs. But when we do that, it means that we have a different interpretation of what the solution is. Okay, so technically you could have done this with these previous questions. But basically what we want to do is when the two sides get a little bit more complex, you can go into your y equals, and instead of like working to move everything to the same side, you can put in each side as its own graph. So I would go into y1 and put in 3x, whoops, why did I do that? Oh, okay, y equals, let's try that again, 3x squared minus 6x plus 5. Okay, and now on the other side of the equal sign, I'm going to put in 2x bracket 4 minus x. And this is just cutting down on our work, right? We don't even have to try and expand this. The whole thing will be calculated for us. So now when we put enter into there, the first graph comes up first, the second one comes up second. So if you have a non-color version of this calculator, just watch which one comes up first and second, and sometimes you could even have like a third and a fourth you could put in, and then you would just watch to see which one is which. In the color one, you can look at your y equals and it shows you the first one, so this 3x squared is the blue one, and then the next one is the red one. Okay, so now when we go to this, I'm going to try and move that out of the way a little bit. So now I have a new way for you guys to do a calculation, because the way we find this solution is to go in and solve for, instead of our x-intercepts, if we have two separate graphs, the solutions are the x values of where those two graphs cross. So if I go second function trace and I go to new function here, intersect, we haven't used that one yet, hit enter. And it's going to say a little bit different. Instead of left bound, it's going to say first curve. So it's basically asking you, is the cursor on the first curve that you want to consider when you're looking for your point of intersection? So again, I always like to get closer to the point of intersection. So I'm just going to say first curve, and I moved over a little bit, so I'm right close to where they cross, and then I'm going to hit enter. Then it says second curve. It should automatically jump to it. And I bumped it closer, you don't have to, but it's going to kind of know that that's where we're at. Hit enter and then hit guess. So we see that the point of intersection is at 0.42. So that's going to be x equals 0.42. Now for our other route, because these graphs cross at a different point, we want to do the same thing. So second function trace, choose option 5, and it's going to say first curve. Make sure you do move your cursor closer to the point of intersection you're looking at. Second curve, it's close enough. Enter, and then guess, enter. So my second one, my x value is 2.38. Okay, I'm going to round that. So, I can like draw this graph. I'm not going to bother for you guys right now, but I do want to, instead of graphing it for you guys, because I know you guys know how to draw these now, I'm just going to show you that even though this is one way of solving it, if you guys feel like it's too much to remember two separate ways of doing this, you can just move everything to the same side and you'll end up with the same answer if you just look for the roots of that graph. So for example, if I wanted to move all this to one side, first of all, I would multiply this bracket out. So 2x times 4 is, 8x. And then 2x times by negative x is negative 2x squared. Okay, and so that's equal to this 3x squared minus 6x plus 5. So I'm just going to get rid of this because I don't really need it if I'm not going to graph it for you guys. So 3x squared minus 6x plus 5. So now I just want to move everything to the same side. I want to keep a positive a value, so I'm going to go plus 2x squared and minus 8x. And that means I'm doing the same thing to this side. So 3x squared plus 2x squared is 5x squared. Negative 6x minus 8x is negative 14x. And then we still have the plus 5. And of course, these have canceled each other out to be 0. So I end up with, oh shoot, you guys, I was off screen for that, sorry. Okay, so now if I go into my y equals, I just want to show you guys that we do end up with the same value. So 5x squared minus 14x plus 5, right? So I go to my graph, and if I look at those zeros, left bound, enter, right bound, enter, I get 0.42 And you can tell just by looking that the next one is going to be 1, 2 and a bit, 2.38. So regardless of which way you choose to do this, you'll end up with the right answer. I can't think of any instance where you have to use them two separately and find the intersection. So it's just if you struggle to multiply things out and everything like that and do this rearranging, the first option I showed you might be best. If this is no problem for you, which hopefully it isn't, then you can use this method if you find that easier, but you can just kind of pick and choose what works for you. Okay, last question before we wrap up today. We have another kind of a profit question, so you can tell by how many examples I've done of this kind of stuff that it's really important you guys know how to do these profit kind of questions. So in establishing a price point for their candy, a company finds they can sell 10,000 candy bars for $1.25. For a 5-cent decrease in price, they will sell 1,000 more candy bars, and we want to find the price that ensures maximum revenue. So keep in mind that maximum revenue in this case is always the vertex. So we need to set up our own equation, which is usually the part that students struggle with most. Remember that revenue or profit, however you want to use that word, and I'm spelling that badly, is going to be equal to how much you're charging for this, for whatever it is that you're selling, multiplied by the number of those that you sell, right? However much money you make is going to be determined by those two things. So whenever you have a revenue problem, you always have to start out by writing a formula for the price and a formula for the number. And they always have this increase or decrease in price associated with them. So basically this, like the formulas are always going to be pretty much the same. So if we look at the price, you're always given a base price. So they are being sold for $1.25. Oh shoot, actually I shouldn't have the dollar sign in there because we're writing our actual function. So $1.25 is the original price. And what they're saying is that you have a 5-cent decrease in price. So remember, our X variable is always how many price decreases there are. So if our original price is $1.25, the price at our maximum revenue will be $1.25 minus 0.05, so minus 5 cents times by however many price decreases you do, which is X. Okay, then our formula for the number that is sold is always going to be the base amount that they give you. So they're selling 10,000 at $1.25. But they will sell, with this price decrease, they sell 1,000 more for every price decrease. So that means they're going to have plus 1,000 times by however many price decreases they do, which is X. Okay, so we see that this is the exact same formula we've used before. Now we just have to actually multiply those out to come up with our formula. So it's going to be 1.25 minus 0.05x times by 10,000 plus 1,000x. 1,000x. Okay, so you would want to just multiply that out. 1.25 times by 10,000 gives us 12,500. And 1.25 times by 1,000 gives us 1250x. So plus 1250x. Negative 0.05x times by 10,000 gives us negative 500x. And negative 0.05 times by 1,000 gives us negative 50, and we have two x's there, so it's going to be x squared. So just combine your like terms there to simplify, and if you want you can put it in the proper order, so we'd have negative 50x squared. 1250 minus 500 gives us plus 750x, and then our number value is just positive 12,500, so plus 12,500. Okay, now this one is solving by graphing. So we can just go in and enter into our y equals negative 50x squared plus 750x plus 12,500. and go to our graph. Now, of course, my graph isn't going to be anywhere close to what we need for this. So let's see. I'm going to do a little bit of a cheat here and think, okay, this was at 12,500. I'm going to go for my Y. I'm just going to go big. I'm going to go 15,000 instead. So Y max 15,000. And I'm going to make my scale 1,000. Y minimum, I don't really need to go down very far, so I'll go -10. And then for my X scale, X is going to be your number of price decreases. So I'm going to go X max would be 10. And you're not going to have negative price decreases. So let's see if that gives us anything. Oh, not quite. Okay, so we're not quite hitting the vertex, so we want to go in and put our window for our Y max. Let's make it 20,000. And maybe our X, no, I feel like that should be good. Let's try that. Ooh, I might do my X a little bit more. So window X max, let's make it 20. Okay, there we can very clearly see our vertex. Okay, so we want to go second function trace. Let's look for our maximum, left bound, right bound. And our maximum is at 7.5 and 15,312. So 7.5, 15,312.5. So then we just need to interpret that in terms of real life. So this is how many price decreases they would have to do to get their maximum revenue. So basically that means if they started at $1.25, they would have to subtract off 5 cents, so 0.05, times by 7.5 price decreases, so 7.5, which is going to give us 1.25 minus this gives us 0.88. If we round up, I think it gives us 0.875 or something like that. So 88 cents is the price they need to charge for their candy bars to achieve a maximum revenue of $15,312.50. Okay, so that's how you would write it out if you were answering this as a written question. And you can look to the filled in notes for the proper, written way that I would expect you to write that on a test. Okay, so you guys have your assignment to work on, which will have some similar questions to this out of the textbook. And that's everything for today. And I will see you next time when we look at lesson 7.3, solving quadratic equations using the quadratic formula. So I will see you then.